Okay, so let's just go through and calculate these recombination frequencies and then use them to assemble a map. So if you add this up, this comes up to 80 out of 1,000, which is the same as 8 map units. Okay. If you add this up, it comes to 130 out of 1,000, or 13 map units. Okay, and if you add all this up, you'll see that it comes to 190 out of 1,000, or 19 map units. So the question now is, how do we assemble a map using these recombination frequency data points? The way to do this, well, the first thing to notice is that all the recombination frequencies in this case are less than 50%, meaning all 3 loci are linked on the same chromosome. Now, if you had any of these that were 50% recombination frequency, then the best way to model that would be to put them on separate chromosomes. But that's not what we're dealing with here, because all of these have a recombination frequency of less than 50. So what you can see is that the smallest interval is between A and B, the next largest one is between A and C, and the very largest interval is between B and C. So the simple way to do this is to put the B locus and the C locus far apart, as the farthest apart on the same chromosome, and then slot in A between them. Now, if A is 8 map units away from B and 13 map units away from C, then it means that it sits between them, because B and C are 19 map units apart. So we'll put A here, and we can say that that's 8 map units, and then A to C is 13 map units. Now, the issue here that we'll have to deal with now is the fact that 19 map units is not the sum of 8 and 13. So some of you perhaps noticed this. And we'll have to work through this now. If you don't understand the next bit, we'll work through how this works to show that this map distance actually is the sum of these 2 map distances. This actually should be 21 map units instead of 19. But on the other hand, if you don't understand how the next bit works, what you need to remember is that the most accurate map is the one assembled using the smallest numbers. Larger map unit values are always less accurate than smaller ones. So these are the best estimates of recombination frequency between these loci, and because this one's larger, it's a more approximate value. So we've assembled this map using the smallest distances, and this is the correct map. These are the correct values as far as we can determine using these recombination frequencies. This 19 map units, let's tackle where this comes from first, or comes from now, and you'll see why it's inappropriately small. There's actually some things that we've missed in our scoring of recombinant versus non-recombinant. We've scored some things that are genetically non-recombinant for B and C, but yet actually have a crossover event between B and C. And what we need to do to appreciate that is actually redraw out what we had before and have a look at what meiosis looks like in the F1 trihybrid, which is what we'll do next. So what you have to do is you have to return back to the gametes that made up the F1 trihybrid. And now what we need to do is we need to model meiosis in this F1 trihybrid starting from the point of synapsis, and now incorporating what we know about the loci. So if we're going to draw synapsis, that's where the chromosomes are replicated and paired, ready for meiosis 1. Okay, now we need to actually draw the chromosomal arrangement of these alleles in their appropriate spot. So the B locus is first. So if we draw this input set, we know that it was a little b, and then a big A, and then a little c. So this is now the alleles that we know are coming in from this input packet, and it's drawn in the order that we know from the previous steps where we determined the map. Now on the other side, we know that it was these alleles that were coming in. a big B, a little a, and a big C. Okay, now let's revisit what the different possible output products of meiosis are, and then describe the events that have to happen during meiosis in order to produce those particular products of meiosis. Okay, so now I've redrawn this chart that we had from a few segments back, and now we're ready to see where this discrepancy in our map comes from, where we measured the B to C interval as 19 map units, but we measured B to A and A to C as adding up to more than 19. Now that we have the knowledge that all three loci are linked on the same chromosome, we can understand the events during meiosis that are producing the different products of meiosis. One thing to look at here is let's start with these different, the ones that are completely non-recombinant. What's happening here is these chromatids are passing through meiosis without any genetic recombination going on, and as a result we know that there's no physical crossing over going on. So all we need, we could think of it this way, if we call this region region 1 and we call this region of the chromosome region 2, we could say that this simply requires no crossovers in region 1 and no crossovers in region 2. And that will explain these output products of meiosis. Let's look at this one here now. A big A with a big B and a little c. So now in this order, so there we go, big B, big A, little c. So that requires a single crossover in region 1. Maybe I'll just put these up here. If we have a single crossover in region 1, what that produces is a big B now physically connected to a big A and a little c, and that's this product here. It also produces a little b connected to a little a, and then a big C, which is the same as that product there. So this requires a single crossover in region 1 and no crossovers in region 2. Okay, let's move on then. Okay, this next one here, we have a big A, let's find the big A, now with a little b, so no crossover here, and then we pick up the big C. So this one is represented by a single crossover in region 2. So here we need no crossover in region 1 and a single crossover in region 2. And that will explain the origin of these gamete types. Now we come to the last category. And in this category, what you can see is we have all the big alleles, all the dominant alleles on the one output and all the recessives on the other. In order to hook up all the recessives together, little b, little a, little c, and conversely all the dominants, big A, big C, big B, big A, big C, you'll see that we need two crossover events. We need a single crossover in region 1, and we need a single crossover in region 2 that affects the same pair of chromatids. Okay. Now what we'll see is that this is the category that's inappropriately shortening that distance. We originally scored the B to C interval, so B to C being the largest interval here. We originally scored the B to C interval as non-recombinant, and genetically it is non-recombinant. But what's going on to make that non-recombinant combination between B and C, and you can see here we have little b and little c are still together, just like they were before in this input, but now we've had two single crossover events that have crossed away from that input, and then back to that input. So these are genetically non-recombinant, but they actually are a double crossover event that's producing them. So not only do we need to include them as recombinants or as crossovers when we're calculating up the number of recombinants in a given column, we not only need to count them, we need to count them twice, because each of them represents 2 single crossover events. So the question then arises, we have these 2 single crossover events that we'll represent as a double crossover event, and these 2 events happen to form what we scored as a non-recombinant product of meiosis. Now, genetically it is non-recombinant, but it's non-recombinant because of 2 single crossover events. And recombination frequency, as we've been measuring it, is simply the number of single crossover events between 2 points. We've been using genetic recombination as a way to detect a physical event. Now, between these 2 loci, genetically, even though they're not recombinant, we have the ability, because of this locus in the middle, to recognize when 2 single crossovers happen to the same pair of chromatids. So, because we're interested in the number of single crossovers between 2 points as a measure of map units, which again we call recombination frequency, because recombination frequency is the easiest way to detect physical distance between 2 points. But because we're interested in single crossover events between 2 points, we need to count these individuals in this B to C total. And not only do we count them twice within this total. So for the recombination frequency between B and C, we would then say that it is these, and twice those. So 34 plus 36 plus 62 plus 58 plus 6 plus 6 plus 4 plus 4 divided by 1,000. And if you work that out, it should come to 21 map units.